And then, so let's continue talking about homework two. There were known issues with homework two. And one thing I just want to make clear with that is these issues are known, and thank you everyone for who either brought it up before or are bringing up the new issues now, like Color Lover. I'll have to look into because I didn't realize there was an issue there. And one more question in terms of homework two, however, is there anyone who has any idea about, so there are some issues like Shapely that it's just a hard to install library. And as I mentioned before, not crucial to the assignment. But with anything else, would you say there were more general issues with Python, kind of getting an environment set up, or was it more particular with the assignment? And I'm asking this in particular because we are going to be using Python again for assignment 4, and then I sort of do try to weigh this course a bit more towards Python than other courses in this program. So it's that part of it is by design. Yeah. So if so basically just keep that in mind that for assignment 4 you will be still using Python, like that's going to be dash specific, and the so you will have to make sure that your Python environment is well suited. And then what else? So Jim's asking if I believe Python is a better language for Viz. It really depends on what it is that you're doing. Just in terms of grammar of graphics, ggplot is an amazing library, and there's a comparison in JavaScript once we get up to that with uh, there's I'm blanking on the name right now, but there's a comparison and there's comparable language in JavaScript where it's more built towards the grammar of graphics, and you're you're performing aggregations within the um, visualization. I believe I mentioned in last meetup that I was pleasantly surprised by some students who were including the aggregations, dplyr functions within ggplot. Like that leads to a pretty well-defined sort of grammar of kind of data manipulation and graphics. And there's not really a comparable library for that in Python. But then sort of the other side of that is Python is more it is more of a general purpose language than R. So it it really does benefit from having access to tools like Flask or Django, and on the web dev side, and then just other libraries for other steps in the data science pipeline. So the answer is it depends. And in a future lecture, we'll go through a few of those characterizations of these languages. Cool. And by the way, I just saw Gracie the echo. So if anyone else is noticing any issues with sound, put it in the chat and I'll try to see what's happening. And then with that, we'll get started with going over assignment 2. And so for today's meetup, we'll mostly just we'll be going through assignment 2, and then I want to spend a good chunk of time going through some content just about just some entry level, intro level web development concepts. So we'll talk about that in preparation for module 3, where we're going to be using Shiny. So it's sort of our first step into interactive data visualizations, and it'll be helpful to get some background in terms of web dev concepts. You don't really need it for Shiny or Dash, but especially as we start getting into JavaScript, it'll be helpful to really view all of these tools in kind of the same spectrum. We're kind of working our way. We're escaping a bit from the data science side of things, and slowly making our way to the web dev side of things. So I think that'll be useful to have some conceptual framework there. So to get started with the homework, we were looking at the Pluto, what's called the Pluto data set. And as I mentioned in the intro to module 2, that's a database that the city of New York puts together of every single tax lot in New York City. So this assignment is meant to do a few things. It's meant to, first go through visualization library packages in Jupyter, in particular using the Plotly package, and then also using data shader, and just in general looking at strategies in dealing with larger data sets. So, when it comes with either pre-processing, what we were doing with Plotly, or just throwing all the data in and seeing how data shader handles large data sets. So to start out, so for this first question, we're examining different sort of blocks of different height buildings. So we want to see when were older buildings built in each of these categories, and want to try to get an idea of the of what might be happening. And I sort of started out the assignment with this naive visualization where we see different years that seem to have spikes, and kind of hinting that this might hint that we may need to think a bit about this data set. And in truth, this is not the cleanest data set. It's and you could, so really what these spikes are suggesting, it's too regular to be economic cycles, or really too drastic, especially when compared to what's happening in the 1980s through 2000s. But then, sort of examining this, you notice that there are certain decades where, like 1920, we have a big spike. 1925, we have a big spike. So this sort of seems to be suggesting that, there's some sort of, these spikes are happening at very regular intervals. And, sure, as many people saw, it's perhaps too regular. So one of the first things that I did, just to get a clear idea of what is going on with the data set, was to aggregate by time. So I mentioned this in the notes of Pandas, that there are general group bys if you're working with categorical data, but with time series data, Pandas has some nice built-in functions for changing frequencies. And Pandas is really, it was created for financial time series, and this is really where you could see that use case coming into importance. So what we're doing here is we're using this 5A code to resample the data every 5 years, and then we're sort of including our aggregation function, just getting a sum. And what we end up with is something, there's still kind of some spikes, but this at least gives a clearer idea of what's happening. So you could see, there's you sort of have a spike of activity just really on the eve of the Great Depression. Great Depression hits, you begin to fall off a bit, and then you kind of taper off as time is going on. And you could interpret that kind of as, there's sort of this initial growth spurt, and then New York becomes a more mature city where there's not as much development going on compared to New York when it was a boom town. If you think about before Manhattan was fully settled, for example, that's the sort of stuff that's happening in the pre-Great Depression times. So now, one way of dealing with this, this is good for kind of removing some of the noise, but one sort of strategy of dealing with these sorts of spikes is creating what's called a cumulative sum graph. So, is anyone familiar with cumulative sum graphs, perhaps in terms of probability distributions? Yep. Yeah. So if you think of sort of a PDF versus a CDF, you have your essentially the CDF is you could see it as the area under a PDF, and for this kind of unclean data set, the CDF ends up, it doesn't get rid of the noise, but it ends up really making the noise less hurtful in terms of the general pattern. And so when you are plotting out data like this, you still have, what were spikes becomes more of a stepwise pattern. And the stepwise pattern is less of an issue in terms of truly understanding this graph. So if we look at, starting out with something like this, this visualization is really unreliable. You have these weird spikes, and if you were to naively just include a graph like this and present it as truth, people would think that there's something really wonky that happens every 5 years, and that's simply not what's happening. Whereas if you look at, this is a little better, but there's still some fluctuations that may lead a graph viewer astray. But when you're looking at a cumulative graph, you still have those discontinuities, or the sort of jumps, but they become just that. They become jumps between between different years, and it's okay. It doesn't detract as much that there are these jumps. Now, can anyone think of another strength of using a cumulative graph that might be helpful for the question that we're looking at right now? So think about what we're looking at for the question. We want to find out within different building height groupings, where is the, when were the earlier buildings built? Yep. So yeah, Justin mentioned that you could see a large expansion in old buildings from 1920 through 1940. And you absolutely can see that. But more importantly, if I look at what I'm measuring on the y-axis here, I'm no longer getting counts. For here, I'm looking at just pure counts of buildings, whereas here I'm looking at kind of, assuming today is 100%, I'm looking at what percentage of buildings were built before a certain date. And this is really, one of the uses of improbability using CDFs versus PDFs. So for the entire city with a graph like this, I could, use the inherent, I could sort of use the interactivity that Plotly gives me and, try to, really look at a cutoff. I could define any cutoff I want and get an idea of which buildings would be considered older. And let me restate that. So if I decided that I wanted to look at the first third of buildings that were built, I could, I could sort of slide along here until I get to roughly a third. Looks like it's near one of these discontinuities, so the best I'm getting is 29%. And I could just say I'm searching for any buildings built before 1925, and that would give me the earliest third of buildings built in New York City. And then that, in combination with with using small multiples, lets me really get an idea of where I would want to send my building inspectors. So I could, using this criteria or using this method, this strategy, I could pick whatever threshold I want, perhaps based on resources I have, and I could get an idea of where to send my building inspectors. So we could start with 10-story buildings, for example, and let's use 50% as a cutoff. We have our 50% cutoff for 10-story buildings at around 1930, whereas for 20-story buildings we don't reach that 50% until the 1960s. Similarly, for 30-story buildings, we end up not reaching that until the 80s. 40-story buildings, etc. And just kind of an interesting caveat, you see a lot of this same thing happening today. So recently, if you've been seeing how if you're living in New York and you've been seeing how the skyline has been changing, you can actually think of a new dimension being added. It's not just simply new super tall buildings that are being built, but it's kind of skinny super tall buildings that are being built. So if I were a building inspector, 30 years from now, I may be checking out these buildings that we're seeing going up now, because these would be the earliest examples of a new form of architectural innovation. In this case, you have these smaller lots, and people are figuring out how to build taller on a smaller lot. So perhaps we would look at things like floor to area ratio, or different measures like that if we wanted to, do a similar measurement in the future. But and then for past past advances, you get you could tell stories like there were certain, but before elevators were invented, there was just a natural limit to how high buildings could be just simply because people aren't going to be able to walk up you know that many flights. They're capped now at 6, but I've actually visited older buildings where you have to walk up to the 10th floor in a purely walk-up building, and that would definitely get tiring after a while. So there's natural limits that the elevator ended up removing, and then you think of similar advances such as steel frame construction or various architectural innovations like that. And for all of these innovations, there's kind of a pioneering, first few buildings that are built. And I'm forgetting the building now, but there's one building in the financial district where it's built using older technologies, like before steel frames, but it has but it's still has elevators, so it's essentially ridiculously thick walls at the bottom and kind of tapering off. And that's an example of a building that, it's one of the first buildings reaching a certain height, and it's probably worth, checking out for reasons like that. So, any questions on that first part before we move on to data shader? Cool. So for data shader, I was a bit more prescriptive in terms of what I wanted everyone to do, because data shader is it's it's a library where it's sorry, the data shader library is still relatively relatively new, and it's I wanted there to be more of a clear cut solution. So in the solution that for the question that we're looking at, we kind of have a defined set of things that we're looking at. So in the Pluto data dictionary, we see that tax assessments are divided into a few parts. So there's what's called land assessment and total assessment, which could be subtracted out to get the assessment of the structure. And if you think of it, so now for this question, I'm asking you to switch roles, pretend that you're a developer, and really what you're looking at as a developer is you have two parts of the value of a property. You have the value of the land underlying it, and you have the value of the property. And if the value of land is high, it's going to be more intensely developed. That's why you have office buildings in downtowns and not in farmland. Farmland is a lower form of it's a less intense utilization of land. So for this, and then for this problem, we were looking at bivariate choropleth maps to solve it. We're looking at two variables, and we're trying to look at the interplay of the two such that we don't get a population effect in them. So that's pretty clearly defined, and let's look at one way that we could have gone about doing that. So for this particular question, I wanted to, I sort of treated this as just a categorical variable. So we have, I sort of use these 1, 1, 1, 2, 1, 3 naming convention, but basically what we're doing, what I'm doing here is dividing it into a 3 tile. So and I just kind of created my key. This is similar to the data shader example of the census race maps, where it's a categorical variable that's being looked at, and you define your color key and then map things out. So let's see what ends up coming up here. So what we're doing, and I'm using latitude and longitude. So I'm going to first set my canvas as such, and then using the data shader pipeline, I'm going to be setting my variables, my latitude and longitude, setting the categorical variable that I'm looking at. With my shade function, I'm going to be adding my color key, and then just simply plotting it out and looking at what happens. Now, and I just included a little note here. So greener means the assessed land is more highly valued. Redder means that the assessed structures are more valued. And we noticed some interesting patterns here. So, we sort of have a belt if we look at Brooklyn and Queens as Manhattan is seems to be kind of properly valued at kind of higher and lower values are mostly aligned. You notice that similarly with some of these white areas, that's where it's where they're kind of both property and both land and structure are sort of lower valued. And then you have some variation. So you do have areas such as more single family home oriented Brooklyn or brownstone Brooklyn. You see that there's higher land values there. You see some areas in sort of more suburban areas of Brooklyn and Queens where the properties are more highly valued, and so you have some interesting patterns that are going on here. Did people come up with similar maps? Did anyone else have any other approaches to a problem like this? Cool. Cool. So with that, we'll move into some talking about homework 3. So for homework 3, we're going to be looking at CDC mortality data across 50 states and DC, and we're going to be using Shiny to do this. Actually, Vega was the library I was thinking of before, but Vega is the JavaScript library that has a really nice grammar of graphics. Vega Lite, rather. So we have our questions here, and I'm not going to go too much into the questions here, but what I do want to go into is talking about just some general, the general structure of Shiny and a few good practices in terms of programming with this. So these two apps that I have, they're included in the GitHub repo, so you'll be able to play with these on your own. And the two that I want to go through are what I call a simple app and then a reactive app. So first, just to kind of provide a general context of Shiny, there's two main big, kind of objects that we're making, these sorts of lists of lists. So there's two objects that we're making. One is called UI, and the other is called server. So and we'll go through some content about this in a bit, but this maps onto some web development concepts of what's called the client side versus the server side. And I'll go into more detail about what that means, but just kind of for the purposes of Shiny, the UI is where you're defining how your apps look. So you can see I'm wrapping it in something called a fluid page. I have things like headers and sidebars, and then within these kind of major groupings, I have different elements. In this case, select input, and let's see what that looks like. So if I run this app, this is looking at housing prices across different metro areas. So this is, just a good example of a multidimensional data set and how something interactive like Shiny or Dash could be used to visualize it. So, really there's a few things I want to highlight here. We're looking at some different variables that you could see affect the graph. So in this case, seasonality and metro area. And there's also this drop down here, which is not affecting the graph, but it's affecting this. It's affecting this this box here. So, and this will give you more of an idea of how that's happening. Now, one helpful way of thinking about these sorts of architectures is to kind of draw it out in a diagram like this. So, could everyone see the diagram that I'm looking at here? Cool. So, with this diagram, we're really summarizing the interactions that are happening within the app. So it is a relatively simple app, but I kind of made it with this slightly more complicated thing here that's not affecting the graph. So if we were to graph out what is happening, we have three inputs. So we have the seasonality, metro area, and housing tier. And then we just simply look at what they're affecting. So the graph is being affected by both seasonality and metro area, whereas the info box is being affected by all three, by the seasonality, the metro area, and the housing tier. And I want to see if anyone could sort of intuit why this sort of structure might be a bit problematic. Does anyone have an idea? It's not super apparent, so feel free to just kind of guess at something. So Justin mentioned the user might misinterpret it. That's definitely a good point. You could sort of see that if I were a user using this app and I were using this housing tier, I may think that something was broken because the graph isn't being changed. So that's definitely a very good point there. But the one I was thinking of was a bit more, it's not visible to the user, or it wouldn't be visible to, yeah, sorry. So what I'm thinking of isn't, it's something that's not visible to the user, but it's more about how the app would perform. And in particular, looking at what exactly is happening when a user is interacting with these drop downs. So when a user is interacting with these drop downs, the way that you could sort of think of it is if I make a change to seasonality, I'm affecting both the graph and the info box. And that's what's expected because the info box is giving me just stats on the data and seasonality is changing the data. So that's to be expected. Same thing with metro area. But think about what's happening with housing tier. If I make a change to housing tier, I'm not affecting the graph at all. And depending on, so there's some missing information here. The missing information is really how, what happens with each of these interactions. And I'm not going to get too much into it now. This is something that, as we get deeper into this subject, we'll be getting a bit more into. But the main takeaway I want to kind of instill here is imagine if the creation of the graph is an expensive operation, whereas the creation of an info box is a cheap operation. So what I mean is, in terms of computing time, it would take longer to create the graph than to create the info box. And in that sort of situation, I would want to avoid recreating the graph as much as possible. And so in this case, the housing tier affecting the info box, I want to make sure that there's not something that is also causing the graph to be affected. And Shiny has a concept of the way that Shiny deals with this is a concept called reactive code blocks. And so this alternative architecture is so let's first so first in an architecture like this, it's not guaranteed that the graph won't be recreated when we interact with the housing tier. What Shiny does is it kind of groups together the code so that you're adding an extra step within the within this reactive block. And what you're essentially what you're doing is you're saying, so in this case, the info box housing tier changes, the info box changes, and then there's nothing really stopping everything else in the app from essentially resetting. There's nothing telling the graph that seasonality hasn't changed. So the graph is going to assume that seasonality has changed. Everything is going to be recalculated, and that graph is going to be redone, right? In this case, the reactive block is only activated when seasonality and metro area are toggled. So in this architecture, if I toggle the housing tier, the info box, it's known that the reactive block isn't being changed. So essentially, the graph isn't being redone, and the reactive block isn't being recalculated, and more importantly, the reactive block isn't triggering the graph to be recalculated. So this has a few benefits. It has back-end benefits in terms of app efficiency, and it also ends up benefiting, it ends up benefiting the developer of the app just in terms of grouping similar code together. So for this data set, you're not going to notice any improvement changes in any of these different apps. But if I were to go with the reactive code, I have an extra I should have an extra select input here. Let me either I'm missing this or, oh, sorry, there it is. So in the server, we have, it's a very small change because this is a simpler app, but what we're doing is separating out the filtering of the data set by seasonality and metro. So that's all happening within this selected data object. And then what I'm doing in my render plot is calling this, and let me take a step back. So in the server object, let me take a step back in terms of structure of Shiny. So these inputs and outputs, they have two arguments here. One of them is the tag, and that tag is how we're referring to these objects. So when I was drawing out this architecture, I was sort of doing that in a more conceptual way, but the way that Shiny is dealing with this is by essentially saying, the input tagged C's is affecting the output tagged plot one. So that's the takeaway in terms of these tags. the Shiny documentation, which should be in the content section, will go through what's happening here. But so basically, the main change that's happening here is I'm grouping some code within a reactive code block. And I'm calling that function, and then, or um, yeah, I'm calling that function with selected data. I actually think, I don't know, I think this may be my addled brain sort of not seeing what's properly happening here. But this may be this may be a bug. I might have wanted to include season selected data up here, but I'll take a look at this when I'm properly fed. And but the takeaway is essentially I'm using this selected data as essentially a reference to that reactive coding block. The so that's where that is coming from, and that leads to efficiency gains within Shiny, and also helps in terms of building more complex apps. For both Shiny and the Dash module, your apps are going to be pretty simple, so you don't have to worry too much about these efficiency concerns. I just wanted to really introduce these as concepts because for your final project, if you're using any of these tools, there's a good chance that your app will be more sophisticated than what you're working on for these homeworks. So your apps are, you'll want to kind of make things a bit easier. The way that you could imagine this is we have just simple input and output, and there's some crisscrossing happening here. But imagine if you had chains where you make you make one selection, and then that adds that sort of chain. Like let's say you're selecting a country, and then you're selecting cities within that country. That's sort of a nested logic where the cities that you're selecting depends on the country that you select. So there's more complexity happening there, and being able to group your code becomes very, very worthwhile there. So any questions on Shiny before we move on to some more general web concepts? Cool. So, so then just to go through some more general web development terms. As I mentioned before, the two main the two main things that we're really dividing things into in web development is client side and server side. So, the way that I'm sort of summarizing it here, and just keep in mind this isn't a web development class, so I'm waving my hands through a lot intentionally because what I'm really trying to teach you is just enough web development to get you in trouble, not enough to become a web developer. If you do, that's sort of outside the scope of this course. But this is really in service of building interactive data products. So the best way to think of it is client side is what's happening on a user's computer in the browser. This is JavaScript. JavaScript is the language that the browser uses. So that's what's happening client side. And then server side is everything else. So this is, it's called server side because usually the browser is making a call to a server and is offloading computation to that server. So things like accessing databases, accessing APIs, whenever you need to retrieve data from somewhere, that's what's going on the server side. To use a silly example, when you're using Facebook, you don't have the entire database of its 2 billion users on your computer. It's accessing it via the server. So that's, and the client side is communicating with the server side. And then just to make some clarifications for our purposes, D3 is this will come more like this will become more of a big deal with anyone who's delving deeper into D3, but D3 is all happening on the client side, and so with Shiny and Dash, the magic of these libraries is it's sort of dividing up the client and server side for you, and that's why these libraries are sort of making this new world accessible to data scientists. But D3 is it's a JavaScript library. It's meant to be used by web developers, data-oriented web developers, and it's so you need to do a lot more thinking about how the data is being parsed. So when we get up to JavaScript, I'll be saying things like, you really want to make sure that your data is in the exact format you want, because JavaScript is, there's no real concept of data frames within JavaScript. You're dealing with more older, like JSON objects and arrays. You're dealing with more primitive data sets, data types. So with the rest of the meetup, I thought it would be helpful to work on a thought experiment that is building on top of what we did in Module 2. So in Module 2, we, and I'm going to just show off some of these libraries that I'm talking through. In Module 2, we use Data Shader, and Data Shader, like if you notice, we were, there's a lot that you need to sort of manually set. You set your canvas, you set your, you're setting a lot of these variables. And then Leaflet is a JavaScript library that, so I'm just going to, JavaScript, or Leaflet is a, Google Maps style, I was calling them Slippy maps in the notes, so it's something, it's a library like this where you could, essentially create your own Google Maps. You could put whatever icons you want. You could have you could have CSS styled info boxes that are showing up, and this lets you, really kind of create a unique experience using JavaScript, creating a Slippy map experience. So this thought experiment, what we're doing is we're kind of combining a concept from Data Shader. So, Data Shader, we were predefining all of these variables. Let's imagine if we were to be able to combine a Leaflet style interface with Data Shader. So, imagine we had actually, let me get the census notebook. So imagine, like, in this census notebook, you'll see different views of the census data, and more importantly, you see sort of a national race map where it's being overwhelmed by the rural areas, the mostly white rural areas. And as we drill down, we're able to get, more. So here, for example, you would not really be seeing what's truly happening in cities, maybe in some of the larger cities, but not truly. And as you drill down, you see what's happening in these cities, how there are, there are interesting racial dynamics happening. And so imagine if this were a Google Map style map. We were able to kind of go into different levels, and more importantly, get these increased resolutions as we're sort of zooming in and out of the map. So using this as an example, you know, this is looking different than this. And what's actually happening, like what Leaflet is doing at its core, is creating what are called tiled maps. So essentially, there's um, these tiles are predefined where at a certain level there's you know Leaflet knows to display a certain tile set and kind of paint them in as a user is scrolling. And so so basically we want that for a data shader. And so our thought experiment is going to be, imagine if we could navigate a data shader plot like we were navigating Google Maps, how would the architecture of this work? And we're going to be this is going to be very hand wavy, but this is sort of a good way to kind of think about these concepts. So the sorts of questions that we should be asking ourselves is, what exactly does a Slippy map do when a user interacts with it? And another way of stating that is, what are the variables that define the state of a map? So does anyone have any answer to like what may define the state of a Slippy map? So let's think about an easy and what did perfect. Yeah, Kevin, that's exactly what we're looking at. So if you think about what sorts of controls a user has when interacting with a map, it's when I'm doing this, I'm changing the center, and when I'm doing this, I'm changing the magnification. So that's absolutely what's being changed there, the magnification and center. So now the next thing to think of is to try to think about how is data shader complementing these needs. So the question to ask there is, um, you know what is data shader taking as its arguments? And so here we have a canvas being displayed, and we also have a a actually, I'm sorry, the canvas is doing both. The canvas is displaying the by giving us the four corners, it's defining both the zoom and the and 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 the center of the data set that we're looking at. So the way to think of this is we're essentially translating this idea of center and this idea of center and magnification to the idea of a data shader canvas. So one more question. This is a rough diagram, similar to the diagrams we were looking at earlier. Which of these is the client side and which is the server side? Yep, that's correct, Adam. So data shader is the server side, and that leaves Leaflet for the client side. So we have that server side and client side. We have, so this is getting into what I was just going through before, where the images, so remember what I said about these tiles. These tiles are pretty much images. I sort of added a little caveat that there are other ways of thinking about maps. but we're not considering vector maps. But so data shader is serving images that are tailored for a given center and zoom. And then as the user is interacting with the app, they're updating the center and zoom. So there's this back and forth that is defining what the app is doing. And this is something that pretty much what we have here. This is this is pretty much how one would go about creating an app like this, where we have this back and forth. We have a user going in and out like this, and there's data being pulled from the server depending on these variables. So, with something like this, we have a pretty clear idea of what our app would look like. So, any questions on any of these concepts? And keep in mind that obviously this is all very high level, but really this conceptual understanding of these concepts will really help as you're working on future projects and as your projects are getting more and more complex. Cool. Cool. So that'll be it then. Good luck, everyone, on assignment 3. And actually, just a few more logistic things. I'll put out an announcement, but along with Module 4, so in a month, along with Module 4, the final project proposal will be due. So just keep that on your keep that in your mind. And then what else did I want to say? Recordings. I posted those, and I was being perfectionist about trying to edit them, and decided it's better to just post them and then to try to edit them to be perfect. So those are posted, and I'll hopefully be posting future recordings more quickly. And then Mariana had a question. Yeah, so Mariana's question is, if the server side uses a lot of API calls and database queries, how do you make sure the client side isn't slowed down? That's basically, the central problem that any web developer is trying to solve. So so you're absolutely right to think that there are, limits, things that you want to think of, but really, I guess the way to kind of think of it is, think about what's being limited on the client side versus what's being limited on the server side. On the client side, you have, really your limit is your sort of going out, each API call is kind of an action that's being taken. So you're making these, API calls, and you're kind of limited by number of API calls. So that's why there's sort of a limit to client side complexity in that way. Whereas on the server side, you have a lot more freedom. So if you think about any modern web app, really, like any social, Twitter, any like web, really any website that you're going to nowadays, you're making calls to, you're doing very complicated, like using Google Maps as an example. When I'm getting, so if I do something like this, let's analyze what happened there. I provided a string. The only thing in the string that I included was New York to Chicago. And then what's returned to me is there's some parsing of the string. So when I said New York to Chicago, Google Maps knew, I was looking to go from the city of New York to the city of Chicago. It sort of directed me to directions. It knew that string was directions. It knew that, that I'm, yeah, it did a lot of things. So, it gave me sort of some smart choices like, do I want to drive? Do I want to fly? How much would that flight cost? And all of this was done really quickly. This is all being done server side. So, what I just did there, it's, sort of, um, using, it's using intense server resources to calculate that, but it's spreading that out over, you have parallelization of servers. So it's, like this is being done in tons of different places. And, that's how you're able to take something simple and, translate it to to a complex action. We're not going to be building anything this complex, but the, you know, like this is kind of, hopefully a way of thinking of what's happening there. But good question. Cool. All right. So I think that's it in terms of logistics. So thank you, everyone, and good luck on assignment 3. And as always, reach out if you have any questions. All right. Good night, everyone.